Okay, good morning. Here's what I'm going to do. I'm going to go over the last couple days of class in two different videos. So here's our first video. What we're going to start with is the idea of what a derivative is. A derivative basically is slope, folks. It's as simple as terms, it's slope. In Algebra 1, you took slopes of lines. So, your y2 minus y1 over x2 minus x1, your rise over run, all of that stuff. Well, we can actually still use that same idea on things that aren't linear, on parabolas, on cubic functions, on weird-looking functions, things with sines and cosines. We can do that, and it actually gives us a good idea of what is happening at any given point in time on the curve. There is two ways to do it. The first way I could do it is if I know 2 points on the curve, I can estimate it using something called the secant line. Secant line basically says 2 points on the curve. I'm going to take the slope between those 2 points, and I'm going to use that as an average. Well, that's what you've been doing all this time. Y2 minus y1 over x2 minus x1. F of b minus f of a over b minus a. Remember, f ofs are always my y's, and these are always kind of my dependent or my independent variables. So that's one way to do it. It's called secant. Okay, it's not exactly great because a lot of stuff could happen between these 2 points, and you're basically kind of saying, well, between these 2 points, the rate of change is this, but imagine this curve kind of shot all the way, kind of came through here, shot all the way down and all the way back up. It really kind of misses that complexity. So the other way we can do it is something called a tangent line. A tangent line does it at 1 point. And what happens is we pick a point, and then we're going to use the idea of a limit, getting really close from the left and really close from the right. And we're going to kind of see what that number converges on. And that's going to be a good idea of what the slope is at that point. So just imagine this curve, if I kept zooming in and zooming in and zooming in, eventually you're going to get something that's going to almost look like a line segment. It's going to look very almost a constant rate of change. This is where we use this other definition. The limit as h approaches 0 of this expression, f of c plus h or f of x plus h minus f of x over h. That is going to be a little bit more, it's work. And I'll show you an example how it's work. And then the other way we can do is we can actually find the limit given a point. So if we're given a point, what we'll do is we're saying as we approach that point from the left and the right, what happens? And what we do is we take the value of f of x minus the value at the point over the x at that point, and that's also going to give us a slope. Okay, it gives us a slope at that point. This first piece gives us a slope, a formula for the slope anywhere. So let me kind of show you how we do this. So I'm going to use the function f of x equals x squared, which is a parabola. So now what I want to do is I want to figure out the derivative. So f prime of x is going to equal the limit as h approaches 0 of f of x plus h minus f of x over h. So what I need to do is I need to figure out what each one of these are. So in this case, f of x is x squared, f of x plus h is x plus h squared, which is x plus h times x plus h, which if you use FOIL is x squared plus 2xh plus h squared. Okay. Now I'm just going to substitute. So I'm going to say is limit, and notice I always write this limit down, so always do make sure you write the limit down, because if you leave it without the limit, it's not truly equal to that, and that's actually wrong in terms of College Board scoring. So that gives me x squared plus 2xh plus h squared. That's f of x plus h minus f of x, which I found out is x squared, all over h. And if you take a look here, I have an x squared and a minus x squared that cancel out. This subtract to 0. I get the limit as h approaches 0 of 2xh plus h squared over h. Bad too. Remember, we always try the number first to see what happens, but if I plug in 0 here, I get 0 over 0. What that means is I need to do a little bit of factoring, take out a GCF up top. That GCF is h, and it's always going to be h. It might have a number as well, but it will always have at least an h. We factor out the h. We have an h up top. We have an h down below. We now have the limit as h approaches 0 of 2xh plus h. I'm not sorry, 2x, 2. There's no h there, my mistake. 2x plus h. We're going to substitute that h in, the 0 in for h, and what we find out is that this guy right here is 2x. That tells me the derivative of this function, f prime of x is 2x. This is going to be basically how I can determine the slope, So let's say, for example, I want to know what is the slope of the tangent, because that's what this is. It's the slope of the tangent line at x equals, let's say, 4. Because if you think about it, when I use x equals 4 up here, that tells me I'm at the point 4, 16. Plug in 4, 16. So I'm way up here on the top. I want to know what the slope of the curve is there. Well, what I can tell you is f prime of 4 is 2 times 4. That's 8. That tells me that when I look at that parabola, so here's my parabola, it goes through the origin, it's right there, and I'm all the way up here at 416. The slope of a tangent line, which would be a line that would kind of like go like that and hit it, the slope of that tangent line would be 8. Okay. And I can actually write the equation of that tangent line. And the way I can write the equation of that tangent line is I use something called point slope form. And what point slope form says is I use this, y minus y1 equals m times x minus x1. I need a point. The point would be x1 comma y1. The slope, I'm going to determine using the derivative. That's my m. So if we look at it, my point here is 4, 16. My slope here from up top is 8. So if I wanted to write the equation of this tangent line, it's y minus 16 equals m is 8, x minus 4. And I stop. I will leave things in point slope form. That's the equation of this tangent line that hits the curve. Okay, that's how we do it. So this can get complicated the bigger your f of x is, but it is one of these things that once we go through it a couple times, we're going to teach you some of the rules of derivatives, and we're not going to need to do this anymore, but you need to at least know where it comes from. And so the other part that we talked about in that first class, or actually the beginning of the second class, is we talked about something called the normal line. And a normal line, what we're going to find out is that the normal line is a line that is going to be perpendicular to the tangent. It's going to be perpendicular to the tangent. So what it means is, if this is kind of my tangent line, my normal line is going to kind of look like that. And if you remember your rules of perpendicular slope is a negative or an opposite reciprocal. So what that means is this is my tangent line up top. My tangent line was y minus 16 equals 8 times x minus 4. Notice my slope here. My slope is 8. If I wanted to figure out the normal slope, the normal m, is going to be that perpendicular. It's going to be the negative reciprocal. So the reciprocal of 8 is 1/8 with a negative sign in front of it. So the equation of my normal line, using the same idea, is going to be y minus 16 equals negative 1/8 x minus 4. And that's how we do a normal line. So that was our first lesson. I'm going to go ahead and I'm going to do another one that'll go over the second lesson using the alternative form of the derivative, and we will see where it goes from there.